Hello, I'm Peter Whidden. Today I'm presenting my project Mote. First, I just want to say thanks to Recurse Center for hosting this, and thanks to everyone for coming out. I really appreciate the enthusiasm and the turnout for this talk. There's a lot of amazing people in the audience here tonight, so I'm really looking forward to chatting with you all. So you may have noticed, the slide is actually running inside the Mote simulation, so it's going to expire as the virtual creatures start to eat it up. Actually, in the first version of this slide that I made, I created the bottom text with way too much density, creating a huge amount of pressure that when I started the simulation caused it to just explode like this. So the things I want to cover in this talk is first, what is Mote? Second, why am I building Mote? Then, how does Mote work? And finally, I want to talk about the future vision of the project. So, what is Mote? Mote is an interactive ecosystem simulation that integrates elements from both games and research to create a sandbox for computational biology, machine learning, and physics. It uses a custom GPU-based physics engine to model the interactions of many simple behaviors at a massive scale, producing a wide range of emergent phenomena. Okay, so that was a lot of words. We'll revisit this later. To start, let's just look at some pretty pictures. Right now, you're watching a virtual ecosystem simulated in real time. There's a lot going on here. For example, there are plants which during the daytime do photosynthesis, which means that they convert sunlight into stored energy while consuming CO2 and releasing oxygen. There are herbivores, which are the little blue guys here, which eat the plants and respirate, so they consume oxygen and release CO2. And there's carnivores, which chase after the herbivores and eat them, and they also respirate and have a longer tail that stores extra energy. There's also fungus, which passively eats leftover things that the herbivores and carnivores haven't gotten to. There's also some of these inorganic kind of work in progress structures which act as substrates for the organisms to grow in and on. And they can create microhabitats as well by creating a form of partial isolation where you sort of get a different environment in some little sub-biome of the greater world there. We can visualize the distribution of, here this is the gases, so this is showing oxygen and CO2, how it's distributed over the environment. We have basically green regions are rich in oxygen and the blue regions are rich in CO2, so it sort of naturally makes sense that there's excess oxygen where there's plants and excess CO2 where there's animals or decomposers. And the way that these the creatures navigate the environment is through sense. So here we can see basically green is showing plant scent and red is showing animal scent, and the gases as well as these scents are constantly diffusing around in the environment. So basically they are released by different organisms or entities, and then they diffuse around and mix, and that sort of like allows resource sharing that's not directly through like touching close type interaction. And they're able to navigate and find food essentially by following the gradient of this scent as it's diffusing out in the environment. We can also visualize the distribution of food in this world. So this is showing, again, green here, this is like dead plant matter, and blue is showing dead animal matter, which is the sources of food after things have died or been killed that things go and eat. And even though these creatures are constantly competing for resources, this ecosystem is actually extremely stable. So as far as I've tested it, it's stable for hundreds of millions of simulation steps, which is months of real-world time. And in this version, there's no explicit evolution or learning happening, but we'll discuss later why this is going to be less and less the case going forward. So You might also have noticed that there's sound. Basically, the way this works is that every single entity can trigger or activate sounds. So there are ones for when an entity spawns in, there's a little popping sound, and clicking and breaking sounds when things are torn apart or kind of explode. Most of the sounds are just my mouth sounds, kind of as a placeholder for now. But when thousands of them are playing, you can't tell that easily. So, and of course, this is all running in real time, so that means that it's naturally interactive. So we can do stuff like push things around. We can delete and remove stuff. We can spawn in entities and structures dynamically. And we can customize their properties, so you can basically like edit the structures and the type of material that you're injecting into the world. And we can also take control of, for example, a single entity to sort of become embodied in this environment. So we can grab things, break it off, toss it, pull things around. This is like a membrane, kind of like a tape measure almost, or like a roll of string that can be cinched together. We can also control a bunch of entities at once, maybe that are connected in a giant blob to just do some joyriding, basically. And bump around into things, displace things in the world. It's kind of fun. You can also actually control a bunch of entities that aren't connected either. You can just be in charge of any number of them, really. And even when you're controlling that many, they can still all individually grab things. So basically, they all try to grab the closest thing, and it ends up creating some really interesting structures. And kind of the way that Mote is designed and its systems to sort of like naturally allow for this sort of like scalability and composability of these elements. These weren't things that were super explicitly designed, but more just like interesting byproducts of its kind of design philosophy. Another random interesting thing we can do here is we can fill up one of these membranes full of stuff to create a lot of pressure, and we could like clip off the end of it and jet out some particles to send it shooting along. This is, again, like not anything that I intended, but just sort of like one of the like fun byproducts of having like a great physics engine that runs at a large scale in your world. And here's doing the same, but with like stringy, wormy membrane elements, which hopefully doesn't gross you out too much. Blasting off. And of course we can explode things, something that you'd naturally want to do, I suppose. It's a larger one. You broke the sound there for a second. We can create chain reactions, so it's like a chain of things activating, causing volatile elements to sort of react really rapidly. We can also build mechanical systems. So I think that video is going to take longer than I want. Create gears. There's bigger versions of this. This is sort of placeholder, but we can also do other interesting things like simulate fluids and pressure, and this is basically a bunch of blobby elements getting sort of forced through these pipes. There's a lot of emergent, like fluid dynamics from this particle system when you basically mix in the right forces at this scale. And we can dynamically adjust about anything in any of the like global parameters of the world. So here we're adding vertical gravity, causing everything to like sort of come cascading down to the bottom there, creating sort of like a vertically oriented world. Things are sort of dangling down a bit. And we can do the same thing but pulling things in towards the center to collapse it all in and create kind of a planet, a ball of all kinds of different life just getting mixed together in there. And we can also graph and visualize different metrics, population changes, resource levels, other metrics inside the environment. This is actually built by a student who, Manu Adupta, who I hired recently for some work on this project. And he's just done a really amazing job. He's got a pretty insane amount of knowledge and experience in GPU programming and Rust and things for someone his age. So been really impressed with that. And there's some really interesting things that you can see from this. It allows us to really easily pick out, for example, these are like predator-prey dynamics here. So we have in red carnivores and herbivores, and basically you sort of see this like following pattern where when say the herbivore population spikes, then you get a carnivore population spike. So this is just like another example of like the emergent dynamics in this world that are really interesting to analyze, and it makes for a really interesting model of a biological system. But besides doing just some sort of like quick analysis in the engine, you can actually build this whole the whole simulation, the whole engine as like a standalone Python library, basically. So you can run the simulation on, say, a server or whatever machine, and basically do automated experiments and pull data out directly as NumPy arrays. It's like just works very naturally for it. It also runs on like pretty much any device. So this is like basically showing it going on a phone, a tablet, a laptop, and a Linux desktop. So with the Microsoft controller, which is kind of annoying, but it works pretty well. So that's a lot of things. Before going deeper, though, I want to give a little bit of background about the motivation of this project, and kind of talk a bit about how it came to be. So this is me in 2013 in high school, teaching myself programming from YouTube in my room. My senior project actually was like building this like particle simulator thing. So actually not so different from some of the stuff that I'm doing now these days. This is good old Java. In college, I started to do some larger scale versions of this. This is like a cosmological simulation of like galaxy formation. So like millions of particles, actually kind of a similar number to what you can run now in real time if you use the right methods, but done in a somewhat different way. And around that time also, one of the really sort of like influential aesthetic inspirations for this project was some work that I did with my friend Alex Miller, Space Filler, who has basically, we collaborated on this project for a art installation that was on the side of this building. Alex did some really amazing work in it, and I got to, this is a thing that I was prototyping in that project back in the day, and he's done a lot of work similar in this space. And it was really, really fun to work on this, but there was a lot of kind of limitations of that medium and that project. It's like time scale, how we were able to basically, like, the format when it's on the side of a building kind of means that you're limited in how much depth you can have evolving over time, and also for interaction. And it was kind of like, it was really fun to work on this sort of simulated ecosystem, but we ended up cutting out a lot of like real sort of like grounded simulation to just sort of make something that looks nice and like is, you know, pleasing at any given moment, but doesn't necessarily have like a real like model of like resource consumption and navigation and those more kind of like interesting biological, physical constraints. And while I've been doing this kind of work for a long time, I've actually also worked on a variety of other projects in like computer graphics. This is Shader Park, a JavaScript library for writing interactive shaders. And this is some neural cellular automata that with some machine learning work that I've done as well. And actually, the project that sort of was the seed for this one in terms of motivation was also not directly related. But basically, several years ago, I started this project where I was training a reinforcement learning agent to play the original Pokemon game. And I made this in-depth YouTube video analyzing the process and highlighted the ways that it's sort of like the AI's learning aligns with and deviates from sort of our own learning processes. And people really connected with this. There was a lot of folks that were really interested in trying to run their own experiments like this. People that were like new to machine learning or even new to programming that were like, this just looks really fun and interesting. I want to like figure out programming to do this, which is awesome. But yeah, this is created a website at one point eventually that allowed all the people training their models to sort of stream their different agents to this collective shared map where you can see everyone's like runs in real time, sort of progressing. Someone's kind of showing off there, I guess. And yeah, so people were really fascinated by this kind of like actual novel interaction of getting to like tweak the objectives of a machine learning model in like their own simulated environment. Most people at this point have, probably interacted with some AI system as kind of like just using the end product, but it's like really rare for someone to actually have any like hands-on process in the creation or training of these things. So I think it's something that people are very like interested and curious about, but it's really kind of like very much a field of experts. There's a lot of like barriers to getting there. And when I originally started this project, I picked Pokemon because, or I picked Pokemon Red because it's this really old game, so you could simulate a lot of time really rapidly. You can run your experiments without having your own data center, and you can see results in like a reasonable amount of time. And that kind of sort of idea, people's response and interest in that was sort of like the first seed of like, what would it look like to create a game, an engine that was designed to make emergent learning behavior as efficient as possible. Because like in existing games, they're made to look good, to make sense for the player, but they're not actually like, yeah, that's not like a thing that is a part of like games. They don't have like learning, adapting agents. They might have AI, but not in kind of the modern machine learning sense. And there are researchers that will make environments that are meant to sort of like induce these things more quickly, but they're not actually like designed to be fun or accessible at all. So it's kind of like a unique combination, I think, to put those things together. So yeah, kind of some of the design considerations for something that would fit that bill is like running at a massive scale is good because you can kind of either parallelize between multiple games that are happening simultaneously, or you can have everything sort of exist in the same world. Basically, to do like machine learning, you need to see like a lot more experience has to happen much more quickly than like how a human would learn. You don't just see something a couple times. That's how these systems work right now. So basically, by having lots of things all interacting at once and very fast, you can have those dynamics emerge more quickly. And if you want it to be something that people can actually use, it needs to like run on a regular device, not like on an NVIDIA data center, like $20,000 cluster. Sorry, not 20,000, probably like 2 million. Yeah, stupidly expensive. It should run on like regular hardware. And there was also kind of this realization too in the design of like a lot of the things that the people that were like new getting into this stuff, actually I have a lot of like same pain points as like real researchers or scientists. Like things should be easy to set up. You want experiments to like happen quickly, see results quickly, and you want to like visualize things well. You want it to be able to like interact with stuff. So that was also like an interesting realization, is how people doing like cutting edge science and people just getting started want the same things. So kind of the choice of how I decided to design this is using a experimental GPU-based engine where everything is simulated on the GPU. This is the computer's graphics card, and there's benefits for this because it means that you can run a really large simulation, and it's also natural fit for the computations that are necessary for machine learning. Those are just like, it's basically just a lot of math, essentially, a lot of calculations that both the simulation and the ML need, the machine learning algorithms need. And GPUs basically process lots of things in parallel simultaneously. They're more difficult to program, but if you can figure out how to do it, they will do a lot more work. Kind of the tech stack that I chose in this is the engine's built in Rust. I use WebGPU, the WGPU library, not with a browser involved at all, just to basically have this like cross-platform general like GPU API for both graphics and compute. And basically the sort of overall architecture of the system in Mote is that it is a parallel graph processor, which means that there are edges and there are nodes. So you can sort of see in the world here that this world is essentially a graph. You have these sort of particle entities and you have edges connecting them. Generally, the sort of like main thing that the graph is used to represent is like a particle spring system, which means particles that like repel, bounce, reflect off of each other, and then the edges of the graph are like the springs that connect entities together. And so they primarily simulate this particle spring system, but they also do other things too. There's other data besides just physics data on the entities that simulates their like internal energy and other like things that like their properties. Same with the edges. They can transmit other arbitrary data between them besides just spring forces. And there's also a background grid which connects the gases and the other elements together. Really quickly, I'm going to try a little live demo. We'll see how it goes to talk about a few of the other design principles that I've used in this engine. And see if I can operate it while looking at it at this funny angle. Okay, so a few design principles that I've sort of used to guide my process in sort of like focusing on what I think is important and interesting. The first one is no facades. And what this means is it's kind of referring to graphics. This is kind of like in response to modern computer graphics tends to have a lot of very sort of like surface level characteristics. It's very easy to take a game engine like Unity or Unreal and load up some world where you get photorealistic lighting and materials, and like it looks great, but then you go to interact with this world and like the actual mechanics, dynamics of the world are kind of like hilariously simple in comparison. And it's sort of like jarring, this disconnect between how it looks and how it actually works. And I'm very interested in trying to just like fully invert that as much as possible by focusing entirely on how things work and just sort of presenting them, rendering them in the simplest way possible. So, for example, like everything in the world in the engine is basically like only rendered if it's an actual like functional part of the environment. So nothing has, like no piece is there because it's not like a physical simulated piece of the world. It doesn't have like some function, even though like colors are like determined by like their functional components. And this might be a principle that I will relax more over time to like get things to look prettier in the end, but in this phase of development, I find it very helpful to stay focused on what I think is interesting or important. Okay, our next one we're losing a little bit, but this says decentralized dynamics, or it did rather. And what this means basically is that the way the systems are organized and interact in this world are not sort of like top down. All of these plants, for example, they don't have like, there's no sort of like logic or code that determines how this whole plant should like behave as a whole. There's no top level thing that's managing the like full thing. It's basically just the sort of like individual elements, like cells of the larger organism interacting with their sort of own dynamics. They can share energy, they can grow if the resources are available, but basically like everything is decentralized in that way, where like if you were to split a plant apart, both ends will be able to keep growing. They're not like there's only one plant system attached to it or something like that. And that's sort of like, it's both beneficial both for the composability of the system, because it means when you recombine different elements that they're going to just naturally function together better, because there's not like this top level structure. They're just the product of these lower level, simpler behaviors. And it's also great for performance because things scale nicely when it's just all these simple sort of elements. It is trickier to design things that way, but it is beneficial. This third one here, all entities are players. This is talking about how we sort of saw earlier that like all of the abilities that the player has here to say like grab onto stuff, to like push things, spawn new elements. These are things that like all of the entities in the whole world can do, and that sort of allows it to like, ultimately we want like interesting like creatures, agents in this environment, like doing like complex behaviors, and if they don't have the same capabilities as the player, that's basically not going to be possible. So yeah, that's that one. The fourth one here is says diegetic interfaces, and what this means basically is that as much as possible trying to have interfaces that are a part of the world rather than like menus and UIs that pop up. Now this is one that I've like compromised a bit already. There are a lot of like menus and things that you can look at. They're kind of meant to be sort of like more development tools. We'll see how far I'm able to like stick with this one, but some good examples of this one are like the fact that these membranes here are like, oops, okay, all right. So I actually didn't mean to do that, but it still is actually, it's sort of intended that even if I make this mistake, it actually demonstrates the principle, because essentially these are all like extendable elements in the world that you can basically pull out and extend to sort of like create a wall, a boundary, and like an individual like entity can just grab it and pull it along without like having to go through some menu or interface like a UI. And there's like a lot of interesting benefits to that, besides that it's just more like interesting and engaging to interact with. Like you get these like fun interactions, right, where because that part of the interface is in the world, if you bump them all together, it causes this huge crazy chain reaction, which would never happen if you were just creating one through like a menu or something. Okay. Back to here. check time. So basically the way that this system is kind of implemented, all these behaviors, currently there's 100 and something that I've implemented, but they basically are kind of a bunch of like fine-grain behaviors that determine like the properties, how each entity like updates itself. So kind of like a really simple entity without like any sort of living or interesting properties would just kind of have like repulsion. It's just sort of like a physics particle. It like is inert matter. But there are, a whole bunch of different interesting ones that we can combine, mix and match. So like the plants, the herbivores, for example, they have their behaviors because they are like the herbivores they follow the plant scent and they eat the plants and they kill the plants. Those are all like individual components, and you can mix and match these. The plants have like a photosynthesis component and that they grow connected to each other, which allows a lot more composability. Talking in terms of like actual sort of like concrete data, this is like the data structure for one of these entities. There's sort of like a particle component which contains like physics properties, and then there's this outer data which contains more kind of like organism data related to like how much energy it has, how much health, how old it is, what generation it is, so the entities actually track like how many like ancestors back they go, and they have room for morphological data as well in there. And then these are the links, the edges that are pretty simple. They basically have just a like reference, a pointer to the different entities, and then some other like physics or behavior components attached to them. Yeah, and I will say as well that basically getting the memory management on this right, as maybe you can imagine, particularly in the GPU programming context, we have all of these entities which are like spontaneously like creating new entities, and then there's like these edges that connect them. To like make that work on the GPU, it ends up being this like pretty crazy process where basically there's like a custom GPU memory allocator that I have that works on basically just like a flat buffer of entities and links that keeps the buffer dense at all times by sort of like marking off elements that are basically need to be deleted, and it finds elements to move into that space. I have a picture to show this, but I didn't get to stick it in here, unfortunately. This is sort of like a timeline of basically all of the different GPU compute passes that happen in a single simulation step. Not all of the labels are readable, but there's ones for updating the background grid, doing the memory management process, doing physics substeps, basically executing all the different like entities, component behaviors. It's something like 15 plus compute dispatches that happen per frame, and there could be potentially multiple of those per frame. For rendering, I can just really quickly show the like render process here. This is sort of like proof of that principle earlier, that it is really simple. There's just like a few passes really. Basically it puts the state field down in the back, and then it renders the edges, the links, by basically transforming rectangles. All of the geometry is composed of triangles, so these are like transformed triangles that then get like stamped out with a shader to have their shape and sort of attenuation, and then it renders the particles on top of that, and then it layers on the UI in one more dispatch, not pass, sorry. And even though I haven't embellished in things like fancy post-processing effects or other like graphics things, it does sort of like carefully render renders edges of the objects using like analytic sort of anti-aliasing so that you get really sharp edges. That's something I didn't get to show, but if you zoom super far into these things, they stay like really, really sharp. So anyway, I want to talk a little bit about the future vision of this project. I have a lot of inspirations. So particularly like sandbox simulation games. For example, like Factorio is really interesting in how many sort of like different like crazy mechanisms they're able to like you can really like build this system that feels like you have to, it feels like programming in a lot of ways where you're like building this thing and you end up with this spaghetti and you have to like debug it and fix it, but it's like very satisfying because you get to sort of like build this whole world. Kerbal Space Program is like another really great one that like has like all of this real like aerodynamics, orbital mechanics that is like, it just feels like fun and casual, but you actually have to develop for like all this intuition for like real physics to sort of explore this world, which I think is really cool. Minecraft is another great example. It has like a lot of stuff going on in it, but for example, just like Redstone is kind of like this whole simulation of like digital circuits, and there's like huge like community around like building stuff in this engine in this world. Here's sort of like a random old one to throw in, but Powder Toy was something that definitely like influenced me when I was younger quite a bit, which is this sort of like one of these like falling sand games that has like a lot of different elements. I remember I was playing this, I put it on the class, or in one of the school computers in chemistry class and was playing it, and the teacher came over and I thought I was going to be in trouble, but she looked at it and it's like, this is fine, you can keep doing this. These games are popular because they're fun. They're not like meant to be educational games. Like people play them, get really into them because they're fun. And they're also curiosity driven, which is something that is really interesting and important to me, that like you can make something that like you are motivated to engage with it because you're just really curious to try something or to understand how it works, and it's not like it's gamified in, I don't know, there's all kinds of like horrible things out there these days in the gaming world that are like not good motivations or ways to engage with them. And they're like creative mediums, like all these things you like build crazy stuff that's like really cool, and they're like very unique kinds of mediums. And they like inspire you to like learn and solve difficult problems. So those are like big inspirations for me. So kind of like my objective is to take what these games did for like logistics, spaceflight, digital circuits, chemistry, etc., and to do that for like biology and AI, to like have this like very fun and accessible like entry point into these things. But like even like sort of like consider these tools as like real tools for science, because I think beginners and researchers actually really want the same thing. So that's the end. If you Thank you. If you're interested in getting involved with or supporting this project, let's chat. Here's my email address. It's not there. I forgot to put it there. Come find me or look it up. Maybe you can find me online. Thanks again for coming out. Thanks for Recurse Center for hosting this. Thanks in particular to Ava and Emily for help organizing the event. And providing really helpful feedback. Do I do questions, or you can say something? Okay.
All right. We have a few minutes. Let me check the time. If we could get the lights back on, we'll go to our Q&A section. Yeah, we have about 15 minutes for questions, and so we'll do some Q&A, and then Peter, I'll ask you to just repeat, a summary of the question into the mic here when you get it for the recording, for all the rest of y'all.
What are some of the most surprising emergent dynamics that you saw that maybe like broke the game or just led you to go, wow?
Yeah. So the question was, what were some interesting emergent dynamics that were wow or broke the game in interesting ways? A couple that come to mind off the top of my head, I guess, in terms of game breaking. One of them is actually this mode, which I really wanted to show, and maybe I can do it really quick here because it'll just be better to see it than to explain it. But if we take all of those components, those behaviors that I was mentioning before, and I was talking about how they were composable, basically what we can do is we can just generate completely random components in a world. And because there's like hundreds of them and they're all sort of like binary flags, you will get, there's like billions of combinations, essentially. Actually, a lot more than that. It'd be, 2 to the whatever number of components there are. So I'm not showing this very well, but essentially these are all like randomized organisms. So I didn't create these things. I can't explain to you like how they work or what they do. Some of them are kind of like broken in that they don't like really follow like energy constraints and just like grow exponentially. This one's kind of funny looking. There was some other, if I had caught that earlier, I probably could have seen some of the more interesting, a lot of the like interesting ones just get overwhelmed by the ones that are like broken basically. But that's something that's like very much like interested, that's like a big avenue for the future, is like randomly generating new organisms, like plants that can move or that eat animals, or like animals that do photosynthesis, like crazy recombinations like that. Yeah, definitely.
So you talked about your previous projects in like reinforcement learning, and I don't think you mentioned it.
Oh. Sorry, keep saying what you're saying.
I might have missed it. How will you apply like machine or reinforcement learning to this, or is that not part of the plan or not part of this project?
Yeah, that's a great question. There's a lot of like, yes. Question was, how will I basically integrate reinforcement learning into this? Basically, sort of the idea is that it's kind of like multi-agent reinforcement learning. We have lots of different critters, and they can each have sort of their own like observation of the environment. Already, there's basically like sort of like a like simple hand-coded model for each of the behavior components, where like they observe their world through like looking at the sense or the resources on like the vicinity around them, and then they take actions in terms of like they can exert a force, or they can like attack a thing, or like duplicate. So that's kind of like the reinforcement learning like framework of like observations, actions, and then like rewards can be based on like you could imagine coming up with different rewards for different behaviors. There's definitely a lot of like interesting technical stuff for like how to like implement that with that system. Probably don't have time to get too far into that now, but it's definitely like something that I'm really interested in, and this is all kind of in support of essentially having this like system.
So life on Earth was unicellular for quite a long time, and then there was like a Cambrian explosion, then you have all this like multicellular life complexity. What do you think it would take for essentially like the Cambrian explosion to happen here?
So the question is, what would it take for the Cambrian explosion to happen here? And I think that's a great question. That's kind of like maybe more or less the question of like the field of artificial life, and like what is kind of like the right system to like efficiently reproduce that kind of like complexity explosion. And I don't know if anyone I don't think anyone knows the answer. Maybe like unlimited compute would help for sure. But definitely like my sort of like approach here, which is definitely a bit different than some other like A-life researcher work, is kind of to have like minimal primitives that are very expressive in terms of like if you have a really small genome, you can have like a lot of different interesting possible behaviors without like the vast majority of like mutations making nonsense. So for example, when we have like all of these like fine-grained behavior components, it means that like getting some new interesting complex behavior is like not too many, like you don't have to like randomly combine like too many elements to create that you have this like very expressive representation where like you can create a lot of different, morphologies, organisms, behaviors with like a very compact representation. I can talk about it more, but that's probably good for now. Maybe someone in the back now.
Hey, so this seems like it sits somewhere in between on the spectrum from like games to research tools, maybe even art projects. I'm curious, like you mentioned some things like Kerbal Space Program or Factorio that have these really complex systems in them, but also have kind of goals that motivate the player to engage with those systems. Do you eventually envision this project as like being a bit more game-like, having some higher level goals that motivate people to engage with the minutia of how this works? Or do you imagine it being more situated in the research tool space where people are setting up experiments in this and seeing how they play out? Maybe something a little bit new?
Yeah, I am open to it. I would say that, sorry, repeat the question, is, what was the question? The question was, do I want to add more game-like motivations or objectives, clear goals, yeah. So the answer is that I'm open to it, but I'm kind of primarily I'm much more interested in kind of seeing how far curiosity can go or be pushed. The example of a Kerbal Space Program, for example, I actually played most of the time that I played that game, it was in the beta before it actually had like the career mode of like any of the actual objectives, where it was literally just a sandbox. You have like unlimited budget and all the parts, and like you don't get anything for like visiting or achieving anything in the world, but it was still like so fun. And there's like, you make up your own objectives. You just like see the thing in the sky, and you're like, can I get there without exploding 1,000 times? Like, probably not, but maybe 2,000 times will do it. Yeah.
On a more systems level perspective, what are like some of the limiting factors of Mote currently? Are you like bounded by the hardware of the device you're running Mote on? And have you like experimented with like multi-GPU settings or?
Yeah, good question. So it was, what are like the system limitations in terms of kind of like the hardware? Yeah, so like any kind of like most modern sort of like applications are probably like limited by like memory bandwidth, and like a lot of the like optimization, especially on the GPU where there's so much compute available, kind of comes down to like, can you make your data structures as small as you possibly can so that they're really cheap to get on and off of the chip, and like really thinking about like ways to do memory layout so that everything is like co-located. That's like very actually challenging to do for like big like unstructured kind of like particle like sparse systems like this. Is a very difficult problem to map onto the GPU. I kind of had to tap some friends that work on like GPU simulations kind of like a lot to get some key insights there. And also different devices have, in terms of like limitations, different devices have like massive range of power to them. So like a mobile device is maybe 1/10 the power of like this laptop, which is like 1/10 the power of like a high-end GPU. So there's definitely like a challenge in terms of like, like how big of a world can you have, how like fast can you speed up time, depending on what device you're on. If everything is like efficient, you can still do like interesting stuff at the smallest scale, but yeah, like particularly multi-GPU, I've maybe thought about it, but I haven't actually like made any plan of how it would be implemented for this. But you could certainly have, lots of simulations running in parallel with a like desktop GPU. You can run worlds that are much bigger than the ones that I've shown here, or run these ones at like 10 times like speed, essentially. Yeah.
I've done some GPU stuff before, but it's always been like a lot harder to debug and to learn, and there's like weird error messages. Do you have any advice or pointers for somebody who wanted to learn GPU programming?
Yeah, okay, the question was, do I have any advice for people that want to learn GPU programming? Yeah, so I mean, I will first just acknowledge that yes, it is not it is not easy to program GPUs. They are harder to think about how you map them, and like just the tooling is kind of crazy. Like different platforms have all this, like have their own APIs for everything. I mean, they're not consistent in the same way that CPUs are. So there's real challenges, but there are definitely like tools that exist that make it easier. There's some new stuff. For example, I'm using web GPU, which means that I can just write one version of my code and run it on any device. There's stuff like CUDA and DirectX and Metal, and like they're great, but like they only work on one platform. So it kind of depends if you want to ship a thing to all of that. Particular tools, the Metal debugger on macOS is quite good, and if you have, say, like another application that translates to Metal, like a Unity application or web GPU, you can still basically use that debugger to sort of like walk through shader programs, like using Shader Toy, where you just have like a simple setup that works a lot to like try things out and get comfortable with is good. And then just like part of it too is maybe just like building tools for debugging kind of as you go. So like if you want to like inspect data state of the program, like having ways to actually like built into your program to get at it without having to use some sort of extra tooling. Yeah. One more.
Can you use this to model other things like game of life?
I guess game of life. Oh, sorry. Yes. Can I use this to model other things, other systems like game of life? I'm thinking about that. I think that there are ways to do that. I think like within this framework, like, to implement like game of life specifically, that's probably something you would like add some code to do. It's not like from just like the interface, the UI. I would be able to.
You can't like you showed gears. Like use that to like have a stick or something like.
Oh well, in that case, like if it's like you could make some like I don't know like a transistor or like some little Turing machine, then you can do anything. Then it's fair game. So like I certainly could not rule that out. Maybe you can. That wouldn't be very efficiently simulating those things. You can actually I did an experiment where I swapped out some of the like particle repulsion code with the formula from, is it Smooth Life or Lenia? I have some videos which I won't dig up right now, but you can definitely like pretty easily hack it to do a lot of these adjacent things.
All right. That's all the time we have. Let's give Peter one more round of applause.